This is a nylon filament. We're going to dip it into water and place it on a flat plate. After it dries and we put the filament upward, the plate is suspended in the air. In fact, it's attached firmly. Let's pull the filament perpendicular to the plate. It separates easily. The ease of removal varies with the direction we pull. The secret is a 2mm spatulate tip. This structure is inspired by a fly's foot pads. However, it's not an exact replicate. In order to reduce the cost, the production process is also inspired by the fly's embryonic growth. Conventional adhesion technology seeks to increase bonding strength. However, due to society's increased focus on recycling, decomposable assembly is required. For this reason, separability has also become important, in addition to adhesive strength. To make this possible, we can learn from creatures. Flies, for example. They're able to climb sheer glass surfaces by sticking and then releasing their feet. This is made possible by their spatulate foot pads, which control the two kinds of forces acting between their feet and the wall. The first is called capillary attraction, which works through small amounts of liquid. You can see this when your wet fingers stick to small things. The second is intermolecular force. When two objects approach each other, the force of attraction between their molecules sticks them tightly together. These two forces are maximized when the foot pads are pulled along the surface of a wall. That's why flies stay attached to a wall. On the other hand, they are able to shift their legs very easily. In fact, their foot pads detach easily if they are pulled perpendicularly to the wall. This is because capillary attraction and intermolecular force decrease sharply as the gap between the objects widens. Flies switch between attaching and detaching their foot pads by moving their legs in different directions. This is one of the many things we can learn from the natural world. This bio-inspired research is called biomimetics. It has produced some novel adhesives that can be attached and detached easily, for example. However, producing tiny, complex structures requires special equipment and a great deal of energy, leading to problematic cost increases. Here at NIMS, one of our biomimetics researchers focuses on reducing cost. Dr. Neo Hosoda is a specialist in adhesion and detachment. She has developed some novel biomimetic adhesive structures. She noticed that insect body structures form from common materials at room temperature. She became convinced that a solution to the cost problem is hidden in insect body formation processes, as insects form complex structures easily and with little energy. She found interesting research showing a microscopic view of metamorphosis in a fly pupa co-published by 2 universities in Japan. She was surprised at the footpad formation process, which suggests a means of cost reduction. Our hairs grow from the root. However, fly footpads grow in the opposite way. In a fly pupa, a tip of downy hair is affixed. The hair is then pulled straight, forming the spatulate footpad. Affix the tip and pull it straight. This method is completely new in biomimetic studies. Dr. Hosoda had a flash of inspiration on how the spatulate structure could be made very simply. First, a pair of nylon fibers is prepared and the tips are affixed with paper tape. They are then dipped into a sodium alginate solution. After they're pulled up, you can see a liquid-filled spatulate shape between the fibers, which are entwined by surface tension. They are finally dipped in a calcium lactate solution, dried, and the unnecessary parts removed. It's a very simple process. Let's observe how it sticks. Moisten the tip and place it onto a flat plate. Wait until it dries and pull the other end of the fiber carefully. The fiber remains in contact with the plate, which remains suspended. However, when the fiber is pulled perpendicularly to the plate's surface, the tip comes off instantly. Contact can be maintained or released by varying the pulling direction. This spatulate surface is extremely flat and adheres flexibly when it gets wet. That's why it behaves in the same way a fly's foot pads do. This structure is easy to prepare, inexpensive, and reusable. Thus, it is expected to be widely used as an environmentally friendly technique. I was delighted to find an easy way to make this structure. Since creatures form themselves using common materials at room temperature, we can learn many things from the ways in which their bodies form. I'm looking forward to the emergence of a succession of new biomimetic fabrication technologies. NIMS continues to develop new eco-friendly technologies inspired by nature.